Hello everyone, welcome back. Today, we want to talk about solving linear systems with three variables. So you probably have done or may seen other videos on solving linear systems with two variables, where you have two variables, and two equations. Now we want to extend that idea up to have three variables, in most cases three equations, though we could have some cases where you have two. So we'll take a look and see how those work, how they're solved, and also what kind of solutions you can have. So our goal is then understand the types of possible outcomes of systems of linear equations with three variables. Be able to solve these systems we use elimination. We can use substitution, but we'll focus on elimination here. And also be able to determine whether a system is inconsistent, meaning it has no solution, or is infinitely many solutions. Now remember, linear means that all our variables are the first power. So let's actually come over here to the right and look at what will be our first example we'll do. You get an idea what these look like. So our directions will be to solve. And so the first one we'll do will be this example. So it's going to be 2x plus y plus z is equal to 9. That's our first equation. Then minus x minus y plus z is equal to 1. And our third equation will be 3x minus y plus z is equal to 9. All right, so here we have a system of three equations with three variables. And generally, if you want to get a unique solution, meaning one individual solution, usually however many variables you have, you usually need that many equations. Let me write this a bit better. These are all kind of lined up. Okay. Now, also, these are still linear because all of our variables are the first power. That's what makes them linear. So when you had a linear equation with two variables, we just said x and y equals a number. That was a straight line. So we go up in one dimension, and each one of these equations will actually define not just a line, but actually an entire plane. So what we're looking for then for a solution is a place where all three of these planes intersect. Okay, so if you once again have three variables with three equations, then here are the possible outcomes. So remember, we have two variables and two equations with linear systems. You had three possible outcomes. You had one unique solution. You had both lines could also be parallel with no solution, or both equations were of the same line where every point on the line was a solution. So as you can imagine, going up another variable, you have more possibilities. And these are what those possibilities look like. So once again, each equation is a plane in space. And so they can all intersect at one point. This point P you see right here in this diagram. That's one possibility. Okay, if they have a single unique solution. Now, that's the only way to have a single unique solution, where just your point is basically one point in space. Other solutions involve basically infinite solutions, but still more specifically, they all meet either a line or a plane. So the rest of them, B, C, and D, are all the ways you have other solutions, where solutions to all three equations at once, but not in a single point. For example, here, we call these planes or these equations 1, 2, and 3 in Roman numerals. They can all intersect in one line, like you see here. That's one possibility. Planes 1 and 2 could possibly be the same planes, and then they can intersect a third plane in some line, or they could actually all be all three equations for the same plane. That's how you can have the solutions. Now, to have no solution or no points in common, there are also, in this case, four different ways that could happen. One thing, they can all be just kind of like with lines, they can all be parallel planes to each other, and so have no solution. They have no point in common. Okay, and also over here, point H, essentially here, planes 1 and 2 are the same, and then they're parallel to plane 3. So there's also no solution. The other cases, you can see, there are solutions to two equations at one time, but not to all three at once. So that's what we're saying here, is all three equations at once. They're not solutions to all three at once. You can have a solution to two at once, but not all three at once, and therefore there's still no solution to the entire system. Okay, that's basically what I say in the wording here below. Those are possibilities. So we have one way to get a unique solution with one point at one point. Three ways to get infinitely many solutions, basically intersect either in a line like these two or in a plane. And then 4 ways to have no solutions to the entire system, although two equations at one time may intersect in a line, but there's no intersection for all three simultaneously. So now let's take a look and actually see how to solve one, and solve one like this one here on the right. So once again, we're going to use elimination method, although you can use substitution. And so hopefully this will be elimination will be fairly familiar to when you've done elimination or the addition method with other ones. what we're going to do is it says we're going to choose a variable to be eliminated, and that's whatever you want to choose. Okay. Now here I'm going to choose. Let's eliminate. Let's call these equations. Come back over here. Call these equations A, B, and C, just so I can have something to call them. Okay. Now it's up to us. It's a choice, but let's pick something simple. You notice here I have a plus y and a minus y. That'd be something easy to eliminate. So let's eliminate y. Okay. So with that choice, then let's just go ahead and add equations A and B. Okay. We add them the way they are. And let's just write them again. So 2x plus y plus z is equal to 9. And negative x minus y plus z is equal to 1. If I simply add those as they are, as you can see, the y is going to go away. My results is going to be 2x, and the negative x is going to be x plus 2z is equal to 10. Okay. Now I have one equation and two variables. So let's back up just a minute. Our problem is that we have three equations with three variables. So we eventually want to get down to possible just one equation with one variable. But first, we need to get down to two equations with two variables. Okay. So now let's eliminate another one. So now I actually want to add, let's do a similar thing. Let's actually add equations A and C. Because once again, we have a plus y and a minus y. That's the easiest thing to do. Although like with the systems of two equations, you might multiply one or both equations by some number so you can add them to eliminate a variable. Let's do that. This time let's add equations A and C. Let's write those down. So A, that's my equation A right there. So 2x plus y plus z is equal to 9. And then equation C, 3x minus y plus z is 9. Is also equal to 9. Okay, so once again, add these. And this one's going to allow us to eliminate y. And so we have 2x and 3x is 5x plus 2z is equal to 18. Okay, so now what we have is we now have a system of two equations and two variables. And we've done that if you see my other videos, you've done that before. Also, you may have done this before in other videos or other classes. X plus 2z is equal to 10. And then 5x plus 2z is equal to 18. Okay. Now, once again, still want to use the elimination method. So let's eliminate, doesn't matter. Let's just eliminate z. That's probably the easiest. So let's multiply, I'll just call it the second equation, by -1. Okay. Multiply the second equation by -1. Oh, that's just a choice, and that will change the sign. So our new system now, first equation is still the same. X plus 2z is equal to 10. Now we have minus 5x minus 2z equals -18. Okay. Now, once again, add these. And this will eliminate these z's. And so we have x and -5x is -4x. This is going to be -8. And now we have one equation with one variable. And this is now easy to solve. And so x then, of course, if we divide both sides by -4, will be 2. So that's the first part of our solution. Okay, 2. Now, we want to find z. Let's go ahead and find z, although we want to find all y as well. So let's find, let's use, say, this equation right here, either one, to find z. So I use this one right here. So x, which is 2, plus 2z is equal to 10. And then, of course, subtract 2 from both sides. We have 2z is equal to 8. And z is equal to 4. Okay, good. Next part. So lastly, we want to find y. Let's go back up, pick one of the original equations. Doesn't matter which one. Okay. Let's see. I think I'll pick the first one. So 2x plus y plus z equals 9. if you choose any one of these, that looks like might be the easiest one to use. So 2x plus y plus z is 9. So use equation A, and then said 2x, and x is 2, plus y plus z is 4, is equal to 9. Of course, that's going to be 4 plus y plus 4 is equal to 9. And of course, we have y plus 8 is equal to 9. And so subtract 8 on both sides, y is equal to 1. Okay, so our solution, so this is a consistent system, because we have one solution. And our solution is a point in space, not just in a plane, but in space, in terms of x, y, and z coordinates. So x is 2, y is 1, z is 4, so a point 2, 1, 4. So we drew a picture of these, or drew a graph of these three planes where they intersect is this point 2, 1, 4. So this would look a lot like this first system right here, this first example, except this point right here where they intersect would be this point, 2, 1, 4. Okay. So that's the basic method. Now, as I mentioned, you can also use the substitution method if you want. I'll just briefly explain how that would work. So basically what you could do is essentially solve, for example, this equation for z, and plug it in here, and also solve, and plug, say, for example, solve, like, say, this equation here for z, plug it into both these other two equations, and that would then give you, since z is essentially be eliminated, then that would give you two equations and two unknowns for x and y, and then essentially either use elimination or substitution from there to do that. That would also work. Okay, so now that's when you have a nice case where it's a consistent system like that. Okay, now let's take a look at a couple examples where you may have either inconsistent systems or you may have infinitely many solutions. Okay, so this is going to be a case. Let's take a look at a couple of cases where it may be one of these other cases here. Okay, either infinitely many solutions like B, C, and D, or no solution at all like these three. So let's take a look at the first example of that. And let me make sure I remember which one I want to choose. So number 2. Let's solve this system. 3x plus 5y minus z is equal to -2. Then we have 4x minus y plus 2z is equal to 1. And then we have -6x minus 10y plus 2z is equal to 0. Okay. Now, let's approach it the same way. Once again, let's call these A, B, and C. Now, this time, I'm going to save us a little work because I know what's going to happen. I'm going to add actually equations. Let's choose one variable to eliminate. And let's say I want to eliminate z. Okay. Okay, so I want to eliminate z. So let's say I want to add equations A and C. Okay, add these two. Now, if I add them right now, it's not going to eliminate z, but first, I want to multiply. Write that better. First, multiply equation A by 2. Okay, if I multiply this by 2, we have -2z and plus 2z. Okay, let's multiply that one by 2. All right, so that's going to be 6x plus 10y minus 2z is equal to -4. All right, just multiply the equation A by 2. Now, let's put down -c, or put down equation C, -6x minus 10y plus 2z is equal to 0. Now, hopefully you see something unusual here. if we add these, okay, so we did in the last example, if we add these, what's going to happen, if you notice, we do eliminate z, which is what we want, but also end up eliminating everything else. So this is plus 0, plus 0, plus 0 is equal to -4. We add those. So 0 equals 4. And if notice, this, of course, is a false statement. Okay. This is false. And because it's false, if you notice, there are no variables left, so there's nothing I can plug in for x, y, or z to make this a true statement. So what this tells us being false is that there is no solution to the system. By system, I mean all three equations at once, okay? So this is an inconsistent system. Okay, because there's no, what it means is these two equations, or these two planes, by A and C don't intersect. Now, like A and B may intersect and B and C may intersect, but these two here don't intersect. There's no solution to the entire system. Okay, so what we have then is something like one of these down here at the bottom, 4. Okay, probably like one of these two right here, since most likely so you're not at the same, you would not get the same kind of a statement, a false statement, if you try to add A and B or B and C. So probably like one of either F or G right here. But still, there's no place where all three equations meet at the same time. So in this case, there's this inconsistent system. There's no solution. Okay. Let's take a look at number 3. Okay. And this one, equation 2x plus y minus 3z is equal to 0. 4x plus 2y minus 6z is equal to 0 also. And then the last one, x minus y plus z is equal to 0. Let's go double check, make sure I wrote those down correctly. Because if I made a mistake, then I might get the result I expect. Okay, once again, call these A, B, and C as before. Okay, now let's pick one to eliminate. It doesn't matter. Let's see. How about I want to eliminate? Let's eliminate y this time. First off, let's eliminate the variable y. So to do that, let's add equations A and B. Okay, the first two. Now, once again, the same thing. If I add them directly now, it's not going to cancel out. So let's actually, then, if I want to eliminate y, this needs to be a -2. So let's multiply equation A by -2. Okay, so multiply equation A by -2. And so that's going to be, by -2 is being -4x, okay, minus 2y plus 6z, okay, is equal to, of course, -2 times 0 is 0. Equation B is still the same. 4x plus 2y minus 6z is equal to 0. Then once again, if we add those, like before, what we see is that, right, so we do eliminate y, which is what we wanted, but also once again eliminate both x and z. This time we get something different. We get 0 equals 0, which of course is true. Now, so we get a true statement. What does that mean? Well, what it means then is there are infinitely many solutions. So this is much like what you've seen before with two equations and with two equations and two unknowns, linear equations and two unknowns. Okay, so there are infinitely many solutions. So basically what happens is like one of these three here. So B is like one of these, B, C, or D. In fact, most likely it's probably, what this tells us, these two planes are actually, these two equations are actually the same. Okay, these two equations are actually the same. So it's probably something like this right here, probably something like C. Okay, actually equation C is not the same as the rest of them. So it's probably something like this, where equations A and B are the same, and then they intersect C somewhere. But either way, you have infinitely many solutions. They intersect either probably in some line, okay? So they intersect. So these equations, or the planes rather, not just really the equations, but the planes, intersect in a line. Okay, so something like that. Okay. Now, last thing I want to talk about. Actually, let me correct this. Let's make sure the word E, this letter E, doesn't look like a G. It's intersecting a line. So that case, so basically, much like what you are probably seen with the equations of systems of two equations with two unknowns, then if you get a false statement, it means you have an inconsistent system. There's no solution to all three equations at the same time. If you get a true statement, when you combine them, that means that at least two of the equations are the same, two of the planes are the same. And so basically, once again, you have infinitely many solutions. And once again, probably, unless all three are the same, which is possible, not in this case, though, probably means something like this, where two of the planes are the same, then they intersect the third one in some line somewhere. Okay. Now, let's look at one last example. And this one, what we want to look at is when you have this is going to be a bit different. So we want to solve this system. Let me make sure I write the system I want. And so this time, instead of having three equations, we have two equations, x plus y plus z is equal to 2. And let's do 2x plus y minus z is equal to 5. Okay. Now this time, obviously, we have three variables, but two equations. So what we expect from this then is either we have infinitely many solutions, or no solution. And what that means in terms of the graphs is that, once again, to have a unique solution like we had in the first example, you have to have three equations and have to intersect at one point. That's not possible since we only have two equations. We have three variables. So either they all either these two intersect in a line somewhere. So imagine this, think of this part F, take the top half of part F where you just have two planes intersecting a line. Because once again, there's no third plane. There are only two equations. Or it's possible they could both be parallel planes like this, two of them, like the first two here, and they have no intersection at all. Okay, but let's find out. So what we want to do then, our directions here want to be, let's say, if infinitely many solutions, I want to write solutions with what's called an arbitrary z. Okay, so to make z, essentially z is going to be like a free variable or an independent variable. Okay, I'm going to come explain what that means. So in order to make z our independent variable, what we're going to do then is we're going to pick another variable to eliminate. Let's pick y. Okay, let's eliminate y. Okay, and so let's call these equations a and b. You have to do that. Okay, so of course we want to add a and b. And since we want to add a and b, once again, can't add them directly, so let's multiply. Let's pick equation a by 1. Okay, since we have a positive y in both cases, just one of them needs to be negative, so we'll just choose a. Multiply equation a by 1, negative 1. Okay, so the first one, negative 1, and that's going to be, since you make everything negative, since everything is positive, and so that's going to be negative x minus y minus z is equal to -2. Okay, just negating everything here. Then my second equation is still the same, 2x plus y minus z is equal to 5. Okay, so 2x plus y minus z is equal to 5. Now, let's add these. Right, we do eliminate y, and what we're left with then is going to be just x, then minus 2z is equal to 3. Okay. Now, what we want to do then is remember we can't, now since we have two equations, we can't add two other equations like we did in the previous example, other two. There's only two. So what I want to do then is since I want z to be my arbitrary variable, I want to solve this for x. Okay. And so it's easy to do. So x, add this to both sides. X is 2z plus 3. Okay. Now, so what this means then is since it's going to be infinitely many solutions, I can choose whatever z I want. This will give me my x. Now I need to find y. Okay. Y in terms of z. Okay. And so to do that, what I want to do is just let's plug this result we just got. Into, I'm trouble writing tonight. Into equation B. Okay, plugging in the second equation. Once again, that's also just a choice. That's what we're going to use. Okay, so this is my x. So we have 2 times x, which is 2z plus 3. Okay, plus y minus z is equal to 5. And now I want to solve this for y. Because now what I have is I have just equations involving y and z. Of course, distribute the 2. I have 4z plus 6 plus y minus z is equal to 5. Which combine your like terms. So I have y plus 4z plus 4 is equal to 5. I'm sorry, that's a z. That's not a 4. That should be a 6. So take that back. Right, that's not a 6. Sorry about that. Okay, so erase this. So I have y, and then I have 4z and negative z. That's going to be 3z plus 6. And of course, once again, solve this for y. So move the constant the other side. So subtract 6 on both sides, and also let's go move 3z. So I have y is equal to negative 3z minus 1. Okay, so subtracted 6 on both sides, give me minus 1. Subtracted 3z on both sides, give me this. Okay, so now what I have is, so what this means, also, since we got an actual answer for this, we didn't get a false statement. That means that this is an infinitely many solution case. It's not, if it's inconsistent, we get a false statement like 0 equals 3 or something like that in the previous example. Okay, since we got this, so we have infinitely many solutions. Okay, we have infinitely many solutions. And here's how we're going to write our solutions. We're going to write solution as a point in space. Okay. So a right is a coordinate, essentially as a coordinate group. Okay. So as an x, y, z. So here's a point in space, x, y, and z. So now this is going to be x. We said that x was in terms of both x and y in terms of z. X is 2z plus 3. Y, we said, is negative 3z minus 1. And then we just have z. Okay. Now, once again, infinite many solutions, I can z be whatever I want. Okay. Where z can be any number. okay, where z can be any number I want, okay? For example, let's do a quick example. Let's see what we get. Let's choose or let z equals 1. See what we get, okay? So if z is 1, we're going to have 2 times 1 plus 3 for my x coordinate, negative 3 times 1 minus 1 for my y coordinate, then z is going to be 1, okay? So I'm going to have here 2 plus 3 is going to be 5. Okay, here I have negative 3 minus 1 is going to be negative 3 minus 1 is negative 4. And then z is 1, so this is a point. This point is a solution. Okay, that point is the solution. So any z you come up with, plug that z in, that would give you a point that's the solution. So we have infinitely many solutions because we can pick z to be anything we want and just plug those in. That would give us those results. Okay, so let's summarize what we've talked about today. So when you're solving linear systems with 3 variables, if you have 3 equations, are basically these possibilities. So you can have one single solution. There are 3 ways you can have infinitely many solutions, and then there are essentially these 4 ways you can have no solution to the entire system. So what we did is we used the addition method, always use the elimination method to find the solution to the system. Okay, so it went from a system of 3 equations with 3 variables to a system of 2 equations with 2 variables. Then when it got down to 1 equation with 1 variable, then basically once we got that, we're able to find our x, y, and z. That was one that was a consistent system with just one solution and 1 point. Then we're able to look at some systems where determine whether they were inconsistent or infinitely many solutions. So just like with systems of 2 equations, if you have a false statement, that means there is no solution to the entire system. If you get a true statement like 0, 0, that means there are infinitely many solutions, although this still doesn't tell you anything about what the solutions could be. And then finally, if you have a system where you have 2 equations but 3 variables, you either have to have infinitely many solutions or no solution. They only get no solution if they're essentially parallel planes. Otherwise, they're infinitely many solutions. They meet in some line, and so the point along the line, unless they're also the same plane, that's also another possibility, though not as likely. And basically, we can write that solution in terms of one essentially arbitrary or free variable, then write the other 2 coordinates in terms of that variable. Now here we chose to make it our z our free variable, but we could have also picked x or y. That's simply up to us. In this case, we chose to pick z, and so that in terms of z is our solution. So pick any z you want, that'll give you a solution that goes with that z. Thank you. Have a good day.